Hi everyone, my name is Pierriccardo Olivieri, and with this video I want to present our work made in collaboration with Mehrnoosh Askarpour and Elisabetta di Nitto about an experimental implementation of discrete time quantum walk using the IBM Qiskit library. Before starting the presentation, just a few words about us. Elisabetta di Nitto is a full professor at Politecnico di Milano. Mehrnoosh Askarpour is an adjunct assistant professor at McMaster University. And I am Pierriccardo Olivieri, a master student of computer science and engineering at Politecnico di Milano. With this work, we want to provide an implementation of two quantum walks model, namely the coin quantum walk and the Szegedi quantum walk for a cyclic graph with 8 nodes. For both of them, we extracted a circuit from literature. Then we provide an implementation using the IBM Qiskit library, and we run an experiment, both in simulation and with a real quantum computer, talking about the results that we obtained. Before starting with the implementation, just a few words about random walks. Random walks are a stochastic process that consists in a successive summation of random and independent variables over a mathematical space. They exist in two types: discrete time if t belongs to the natural set, or continuous time if t belongs to the real set. Here we focus on discrete time random and quantum walks. And to give a more practical example, we can consider the image below. Here in the image, we can see our mathematical space defined by the line of the natural number, positive and negative. We have our walker that is actually in position 0. What we want to obtain is a random path. This is achieved by performing a random experiment. That could be, for instance, a coin toss, and depending on the outcome, we will decide to move the walker on the left or on the right. This is achieved in practice by increasing or decreasing the position by 1. Repeating many steps of this procedure, we obtain a random path over this mathematical space. Quantum walks are the analogues of random walks, and in literature we can find different models, each one defining its components in a different way, as we will see in this presentation. And so we can start with our first model, that is the coin quantum walk. In the right, we can see the cyclic graph with 8 nodes and also the binary label. To encode the position, then, we have to encode 8 digits. And so we can use 3 qubits, a vector of 3 qubits, to encode them in a binary way. At the end, we obtain, for instance, for node 0, a vector of 0, 0, 0. The coin is a vector in a two-dimensional Hilbert space. This case can assume value 0 and 1. And the shift operator is the operator that will increase or decrease the position by 1. The mathematical space is defined as the Kronecker product of the Hilbert space of the position and the Hilbert space of the coin. And finally, we can obtain this coin quantum walk as a single operator, U, composed by the shift operator and the coin operator. This is our final circuit. We can identify the 3 qubits at the end that are our position. The first qubit is the coin. Then we have our coin, that is this Hadamard gate, and 2 sub-circuits here that are called increment and decrement circuit. Together they form the shift operator. And basically according to the outcome of this first line here, in which the coin can assume two values, only one of these two circuits will be activated. The Hadamard gate coin is very simple. We just have to apply an Hadamard gate on the first wire, and different type of coin exist in literature. Then we have the increment circuit. Basically, it increases the position by 1 of the last 3 qubits. This image on the left shows the complete increment circuit. As we can see, it is composed by a succession of controlled and multi-controlled NOT gates. In the right, we can see the code to construct them using Qiskit. It is worth to mention the function MCT, which is used to construct multi-controlled NOT gates with more than 2 controls. Here we can specify the controls, the target, and then the mode. That in this case is no ancilla. It is the mode to construct the multi-control top-Fourier gate, as we will see in also in next slides. The decrement circuit is very similar to the increment circuit. Its behavior is the opposite. It will decrease our position by 1, and this is achieved using negative controlled gates that will activate for different input than the controlled NOT gates. These are achieved using these equivalents in which we put a NOT gate before and after a control, and this is why here we have this final decrement circuit in which we apply these equivalents, and the code is also very similar to the increment circuit. And then we have our final circuit, and the link of the source code and the Kirk simulation can be found on the paper. And now we can see the results that we obtained. We performed 5 experiments. The image on the right shows the averaged results that we obtained. We used as backend the IBM Q Athena, and we choose this one because it was the one with at least 4 qubits and the highest quantum volume of 32. For each experiment, we performed only one step of the work. And by looking at the image on the right, we can see in the x-axis our labels that are the node of the graph. And in the y-label, in the y-axis, the probability to find the worker in a given node. Black bars represent the simulation results, and white bars represent the real quantum computer results. So starting from position 0, we expect in a simulation a 0.5 probability to move in node 1 or a 0.5 probability to move in node 7. Looking at the result of the real quantum computer, unfortunately, we have an outlier. Did we have the highest probability on node 1, that is correct, and we expect the second highest probability on node 7, but unfortunately it is on node 3. So we assume that is due to noise. Now we can talk about generalization and scalability. Our implementation is specific for 8-node cyclic graph. So we can change the graph for different families of graphs and also increase it in graph size. In literature, we can find different examples of graph families, such as the torus or complete graph. But in either case, so in changing the graph family or the graph size, we have to alter the circuit accordingly. And for what concerned the graph size, it came with a cost to increase the size, because we have also to increase our succession of multi-controlled Toffoli gates, and they are very expensive in terms of resources, as we will see in the next slide. Here we reported two examples from two approaches from literature. The one of Nielsen and Chuang on the left, and the one of Barenko on the right. They basically express how to construct multi-control Toffoli gates with more than two controls. Here on the left, the approach of Nielsen and Chuang uses the ancillary qubits that are working qubits used only to construct the gate. We can see them on the last part of the circuit. Basically, this is the construction of a 5-controlled multi-Toffoli gate. To construct this gate, we need additionally 4 qubits. And so this is why it's very expensive. The other method to construct multi-control Toffoli gates is the one of Barenko. Here, this is shown an example of a 3-controlled multi-controlled gate. And now we can see that we have no ancillary qubit. This is the no ancilla method, but the circuit scales in depth. And we choose this approach for our implementation. Then we can talk about our second model, that is the Szegedi quantum walk. Szegedi quantum walk is a quantization of a classical random walk or Markov chain, but now the walk occurs on the edge of the bipartite graph. The bipartite graph is a graph obtained by the initial cyclic graph by duplicating the set of nodes and connect each node with its neighbor on the duplicated set. We will see an example in the next slide. The Szegedi quantum walks element are the position that now is composed by the two registers R1 and R2. Then we have the swap operator and the reflection operator. They are kind of complex to report on this slide, so the interested readers can look at them on the paper. And then we have the mathematical space that is composed by the Kronecker product of the Albert space of the register 1 and the Albert space of the register 2. The register R1 and R2 have the dimension of the encoded nodes. So in our case, they have dimension 3. Again, the one-step Szegedi quantum walk operator can be expressed as U. It is the swap operator and the reflection operator. The graph representation in Szegedi quantum walk is done by an adjacency matrix A that is then used to build the transition matrix P, that is the matrix representing the transition probability to a node to their neighbor. The initial state of the walker is given by phi of 0, that is equal in this case to this vector. This vector represents the position 0. Indeed, we have the same probability to move on node 1 and on node 7. This initial state is prepared in register R2 before the circuit, and the expected output is given in register R1. Now we can see the final circuit. Here we can identify the first 3 qubits as the register R1. the last 3 qubits as register R2. Then we have the reflection operator, and at the end we have our swap operator. It is interesting to notice that the first 3 subcircuit here and the last 3 subcircuit before the swap operator are called L and R subcircuit, and they perform a cyclic permutation of the input vector. They are very similar, and they remind the increment and decrement operator. They are a succession of increment and decrement operator because they are composed of a succession of multi-controlled Toffoli gates. And finally, we can talk about the results that we obtained. We performed 5 experiments averaging our results. The image on the right is similar in the structure as the one of coin quantum walk and represents the results that we obtained. We used as backend IBM Q Melbourne 16, and we choose this one because given our account type, this was the only backend with at least 6 qubits. This is the number that we need for Szegedi quantum walk. And so we choose this one with 16 qubits and a quantum volume of 8. Again, we performed 1 step on the IBM quantum computer, and here we have on the x-axis the labels and the probability to find the walker in a given node on the y-axis. Again, in the simulation, we have a 0.5 probability to find the walker in node 1 or 7 on the next step. And unfortunately, for what concerns the real simulation, here we have the results that are very, very distant from our expectation. Assuming that is correct, assuming that our implementation is correct, we assume that this is due to noise. And now we can conclude this presentation. With this work, we want to provide, we propose an implementation for these 2 quantum walks model, and we shared the results that we obtained by simulating in Uriel quantum computer these 2 models. This work is just a starting ground. Talking about the future, our aim was to build a library for quantum walks models to make them accessible to everyone. But for sure, this is an ambitious goal, and this work is just a starting ground to do more experiment, to understand better this field, and also to understand the limitation that we have currently with the available quantum machine. So, presentation is finished. I thank you for your attention, and bye.